Welcome to the Optimization Lab. Today, we're going to use the power of Google Gemini to solve a business optimization problem with linear programming and Google Gemini. You are now a strategic consultant. Our client, the Burger Boutique, needs your expertise to find their most profitable production mix. Your goal is to maximize total daily profit while navigating financial, physical, and market constraints. We will use Google Gemini to translate a complex business crisis using a linear programming model, which is a mathematical method used to find the best possible outcome, such as maximum profit, with linear relationships and constraints. Visualize the results and make high-stakes decisions. Your task is to determine the, quote, optimal production mix and set the Burger Boutique on a path to maximum profit. We have two products, the Classic, which is low cost and reliable, yielding $8 profit, and the Wagyu Special, our premium item with a high margin of $14 profit. The challenge is balancing them to maximize our overall earnings. In the real world, every business operates under limitations. We need to define these limits to solve our optimization problem. The Burger Boutique faces key constraints: a cash budget of $1,200, a specialty bun limit of 80, 100 pounds of beef, 2,400 minutes of labor, a market demand requiring at least 50 classics to be sold, and maximum food storage of 5,000 square inches. We must express these as linear inequalities. Our goal is defined by the objective function. Maximize Z equals 8C plus 14W. This is our profit target based on the number of Classic C and Wagyu W burgers produced. With the problem defined, we now use Gemini as our powerful optimization engine to crunch the numbers and find the solution. We don't just ask for an answer, we provide the AI with the complete set of constraints we just defined. This master prompt ensures the AI acts as a business analyst and solves the optimization problem accurately. The analysis is complete. The optimal mix to maximize profit is to produce 106 classic burgers and 80 Wagyu specials. But this is only part of the story. This production mix yields a maximum daily profit of $1,968. The real business insight, however, lies in understanding which resources were fully utilized and which were not. If our client tries to make 81 Wagyu burgers, the AI will point out they have no buns. If they try to make 107 classic burgers while keeping 80 Wagyu, the AI will point out they have exceeded the $1,200 budget. The point is, 106 classic and 80 Wagyu burgers are the maximum the business can produce before a constraint breaks. To fully understand our constraints and opportunities, we need to visualize the solution. We instruct Gemini to use Python to generate a linear programming graph that clearly plots our constraint lines, starting strictly at 0 to represent positive production quantities. In linear programming, focusing exclusively on positive values aligns the mathematical model with the physical reality of a restaurant. Since it is impossible to produce negative inventory, clipping the chart at 0 ensures the feasible region exists only where both burger types are greater than 0. By eliminating negative clutter, you highlight the non-negativity constraint, making it clear that business decisions are within these logical walls. The visualization captures the operational boundaries. It ensures that we see exactly where the business is constrained. This chart provides a clear view of the feasible region. By focusing exclusively on the positive values, we strip away the distraction of negative coordinates that have no place in a real-world kitchen. Very good progress was made in identifying that inventory cannot drop below 0. This boundary makes it clear that the world of the restaurant exists strictly within these axes. The boundaried space, the yellow shaded region, is where your decisions live. Notice it starts at C equals 50, representing the non-negotiable demand of your lunch crowd. The binding walls, the optimal point at 106 and 80, sits at the intersection of the budget line, gold, and the bun limit, red. These are your two active bottlenecks. Even though you have plenty of beef and labor time, you cannot move higher or further right without more cash or more buns. The optimal point lands where the budget line and the bun limit line intersect. These are our binding constraints. We maxed out on cash and specialty buns. The leftover beef and labor are known as slack. In this analysis, slack represents your unused capacity. A slack value of 0 indicates a binding constraint, a bottleneck that is actively preventing you from increasing your profit. The data tells a clear story of a resource imbalance. You are currently hitting a double wall, consisting of your cash budget and your specialty bun supply. While you have significant slack in beef and labor, enough staff time to prep for nearly 15 more hours and enough meat for an additional 160 burgers, you are paralyzed by the lack of buns and the liquid capital to procure other ingredients. To improve these outcomes, you should not focus on hiring or fridge expansion. Instead, you should investigate if the bakery can deliver more buns, or if a small increase in daily budget could unlock the high volume of meat and labor you already have in the building. Now that we know exactly where the walls are, we can develop strategies to break through them and achieve greater scale. This visual confirms the math. If you want to increase that $1,968 profit, you should not invest in more storage or hire more people. Instead, you need to push the gold budget line or the red bun line. This chart is a powerful tool to show you how to identify where a business is stuck and how to plan for growth. The lab is complete. You've used AI and linear programming to master the math of the kitchen and determine the path to maximum profit. Great work.